Today I am going to explain to you how to form a partial differential equation which is from Unit 2 of differential equation. Now partial derivatives arises when there are two or more independent variables. For example, if I take this equation, z is called fxy, where x and y are the independent variables and z is a dependent variable on x and y. Then in this case, the derivative of this equation 1 will be given by dz is equal to del f del x into dx plus del f del y into dy. That is the partial derivatives of f. You differentiate first f with respect to x and then f also with respect to y. So now let us take this notation. Now del f del x is denoted by p, which is same as del z del x, because I represent z as f of xy. So p represents del z del x, which is same as del f del x. Similarly, q will be equal to del f del y. That means this one will be represented by q, which is same thing as del z del y. And the second order partial derivative with respect to x first and then later with respect to y, that is del 2z del x del y, will be given by the notation s. Del 2z del x2, that is a second order partial derivative of z with respect to x2 times, will be r, and del 2z del y2 is equal to t. See, these are the notation for the partial derivatives of first order and second order. Now let me define you the definition of order of partial derivatives. The order of partial differential equation is defined as the order of the highest partial derivative occurring in the partial differential equation. So it is defined in this way. So let me just take this particular example. If I consider in this case del z del x plus del z del y is equal to z plus x, then the order of this one will be equal to 1. And in this case, the order of this will be equal to del 2z del x2 is equal to 1 plus del z del y the whole square. The order of this one will be 2, because the highest order partial derivatives, the order of the highest order partial derivative is 2 here, so it will be 2. And in del z del x the whole square plus del 3z del y2 is equal to twice x del z del x. In this case, the highest order partial derivative is of order 3, so therefore the order will be 3. And then what is degree? The degree of the highest order partial derivative, the degree of the highest order derivative which occur in it after the equation has been rationalized will be called as the degree of the partial differential equation. So for example, now in this case, if you take this equation del z del y plus del 2z del x2 is equal to z plus 2y, then what is the order? What is the degree of this one? Even though the order is of order 2, but what is the power of this order 2 here, partial differential equation? It is 1. So the degree will be 1 in this case. Now in the next one, del 2z del x, del 2z del x2 is equal to 1 plus del z del y whole raised to half. That means under the square root. So on squaring both sides this one, because you have to rationalize first this one. So you'll get del 2z del x2 the whole square. This will be equal to 1 plus del z del y. Now what is the order, or what is the degree or the power of this highest order partial derivative? In this case it is 2, so therefore the degree will be 2. Now next, in this one, del z del x the whole raised to 3 plus del 2z del y2 the whole square is equal to del z del x. But this is the highest order partial derivative present in this particular case. So what is the degree of this one, or the order of this? It will be 2 again. So this is the definition of the degree of the highest order partial differential equation. Now there are two types, type 1 and type 2, where we can form a partial differential equation. The first one is we can form a partial differential equation just by eliminating the constants. And in the second one, in type 2, you will see that you have to form a partial differential equation by eliminating a function. So first of all, let us come to this one. This take as equation 1. So you differentiate this one partially with respect to x and y. What we'll have now, it will be del z del x will be equal to a differentiation of x here will be 1 into e to power y. E to power y will act as a constant, so e to power y will be a constant, plus it will be only this one because there are no x present in the second and the third term, so it will become 0. So this implies that del z del x is equal to a e to the power y. Now when you differentiate this equation 1 partially with respect to y, what you'll get, it will be del z del y is equal to ax will act as a constant. Differentiation of e to the power y will be itself e to the power y plus half a square. Then differentiation of e to the power y, here again it will be e to the power y. Differentiation of b, which is a constant, so it will be 0. So now this is equation 2, this is equation 3. Now let us see from this. We have to eliminate, b has been eliminated, but now we can eliminate this constant a also from this equation, from this 2 and 3. Now just see from equation 2, what we have is del z del x is called a e to the power y. But del z del y is called ax e to the power y plus half a square e to the power y. This one is equation 3. Now how will you eliminate this one? So let us see from here what will be a square. You can from equation 2 you will see that you will get a square, that is from this it will be equal to del z del x the whole square, then divided by e to the power y square. So it will be 1 by e to the power 2y. So cross multiply this e to the power y this to this side, and then square it on both sides, you get the value of a square. So a square e to the power y, this will give you a square. Then you can cross multiply one of this e to the power y to this side, you get e to the power y is equal to del z del x the whole square into 1 by e to the power y. Here it is 2y, since we have cross multiply one of that one to this side, then you'll get a square e to the power y will be this one. So therefore what you need to do now, replace the value of a e to the power y by this one, del z del x. Now equation 3 will implies you del z del y is equal to x will remain there, but a into e to the power y, you can replace it by this term, so it will be del z del x plus half into what is a square e to the power y. A square e to the power y is del z del x the whole square into 1 by e to the power y. So this is the required partial differential equation after eliminating the constant a and b. Hope it is clear in this case. Now let me solve one more problems related to this one, this type 1. Find the partial differential equation of all spheres of radius lambda having center in the xy plane. Now we know that here the equation of sphere having the radius lambda and having the center as h, k and l will be given by x minus h the whole square plus y minus k the whole square plus z minus l the whole square is equal to lambda square. That is from coordinate geometry. But in this case the center lies in the xy plane. So if the center lies in the xy plane, that means the z coordinate will become 0. So therefore the center of that plane or center of that sphere will be hk 0. Now therefore the equation of this sphere will be given by the equation x minus h the whole square plus y minus k the whole square plus z minus 0 the whole square is equal to lambda square. So you simplify, you get this one. Now differentiating one partially with respect to x, then you'll get what? It will be 2 into x minus h plus differentiation of this will become 0 plus differentiation, since z is a variable which is a dependent variable on x and y, so it will be twice z del x is equal to 0. Name this as equation 2. Next you differentiate again this equation 1 now with respect to y, then you'll get 2 times of y minus k plus 2z del y. This will be equal to 0, equation 3. Now 2 can be cancelled, 2 can be cancelled. So you'll get what is x minus h. X minus h will be, transfer this term to that side, will be minus z del x, and from equation 3 you'll get this 2 will implies, 3 will implies this one. Y minus k will be equal to minus z del y. Now we have to eliminate this h and k from this equation 1. So we know what is the value of x minus h, it will be this one, and y minus k is this. So substituting the value of x minus h and y minus k in equation 1, then equation 1 will imply what? It will become now x minus h will be minus set del x, it will be the whole square, plus y minus k you replace by this one, it will be plus minus set del y the whole square, plus set square is equal to lambda square. So now simplify this one, then you'll see that this minus sign will vanish because whole square, so it will become set square del x the whole square, plus set into set square del y the whole square, plus set square is equal to lambda square. Or set square, what is del x? It is represented by small p, that is p square, plus set square, this del y from that notation in the beginning I have mentioned, it is cube square, plus set square is equal to lambda square. So this is the required partial differential equation formed by eliminating the constant h and k, which represent the center of the sphere in the xy plane. Now in the previous problem, it's okay. So here we are able to find out the partial differential equation by eliminating the constants h and k. In the previous one, we tried to eliminate the constant a and b present in the given equation. So you have to differentiate it with respect to x and with respect to y. Sometimes you will see that you need to differentiate it 2 times with respect to x or 2 times with respect to y in order to eliminate the constant present in the given equation. But in this particular case, you have to eliminate that constant just by differentiating it once with respect to x and once with respect to y. Hope it is clear now with respect to type 1.